Graphing Linearization. This lesson is going to talk about what you can do with a graph that is not straight. What does that mean? Many times you'll find that when you plot your relationship of your data onto a graph, and sometimes you don't find that the points align in a straight line. Oftentimes when we have a straight line, it's easier to analyze the graph because we can take the slope, the y-intercept, and then do our calculations from there. But for a curved graph, it's oftentimes a lot harder. So instead of trying to find the tangent of every single point on your curved graph, what we'd like to do is we want to linearize the graph. So this lesson is going to teach you how to take your data set, replot them so you get a linear relationship, as well as figuring out what the slope of that linearized graph represents. Before we do that, let's take a look at a few examples of graphs you may have seen before. One standard line, you're used to, say, a line. This is something you've seen before. The standard equation for this line is y equals mx plus b. We want our linearized graph to look like this, and we'll talk more about that. So that's the one we're used to. But let's think about a few of the curved graphs you may have seen in math before. You may have seen this one. Do you remember what the formula for this graph is? Well, if you recall, the basis of that graph is y is equal to x squared. How about think of another one? Let's think of one, maybe you may have seen this one, this graph over here. Do you remember what this one can be represented as? If you're thinking y is equal to square root of x, we're on the right track. Also, if you do want to know, there's another way how to represent this is x to the power of 1 over 2. That's another curved graph you might see. Let's take a look at another one. You may have perhaps seen a graph that may look like this. And if you were thinking of this graph in the form as y is equal to 1 over x, you are bang on. There's no room to draw the other part of this graph, but that's okay. We'll just draw this part. And another way to represent this is x to the negative power of negative 1. These are all examples of curved graphs. You might see that it's very hard to analyze them. Take a look at the graph that you made for this particular lab that we did in class. Which one of these graphs above do you think best fit your set of data? When you're thinking through this, you are doing the process of which you're trying to find the best mathematical model to help you analyze your data, to help you show a particular relationship. And that's what we want to do. We want to find the relationship between one property and another property. We are indeed modeling. If you are thinking the best model for your graph is y is equal to square root of x, you are on the right track. So, as I talk about, it is better to linearize your graph, straighten out your graph. It makes it easier to calculate the slope from a linear graph than a curved graph. And a graph in the form of y is equal to mx plus b is much easier to measure and analyze. We're going to look at an example. Example 1. Let's say we want to figure out what a is in y is equal to a times x squared. How do we convert a graph like that to in the form of y is equal to mx plus b? Then later on we can figure out what does the m mean in the linearized graph. I'm going to tell us about this first one. I'm just going to tell you that in here we're missing one column, you might have noticed. What you're going to want to do here is first you want to take all your x values and you're going to square them. I'll talk about why we want to do this later, and you're going to do this through experimentation and understand why we do that through experimentation. What you're going to do is in your first graph that you see in front of you, you're going to plot y versus x. So you're going to plot the first column with the third column. In the second graph, you're going to plot y versus x squared. So plotting your second column versus your third column. I am going to do that as well, and then in the end we can compare what our graphs look like. So this is a good time to pause and do that step if you haven't done so. Okie dokie, so hopefully you have your graphs already. On your graph, you may have noticed that the two trends on either one look different. Now, a little bit of heads up, making sure when you're doing your graph, you want to use as much space as a graph as you can, making sure you have a descriptive title, you have your axes labeled properly. And here, I've just included the best fit line for us to better visualize this. Now, here's the interesting thing. On the first graph, when you plotted y versus x, you got a curved line as what's predicted by our equation. However, when you plot the x squared as what you see in your equation, by the y, you all of a sudden get this nice straight line. Isn't that interesting? Now you might be wondering, ooh, so why does that happen? How does that happen? Why does it work? Here's a little mathematical explanation of how this works. I'm going to zoom into here. Let's take a look at y is equal to a times x squared. And let's take a look at your y is equal to mx plus b, but instead, we're just interested in this over here. No b, no intercept. Look at how this might compare with y is equal to ax squared. In the first graph, we plotted the y with the x. In the second graph, we plotted the y versus the x squared. So we plot this whole thing. If we plot this whole thing as x, wouldn't that convert our equation to y is equal to mx or, whoopsies, ax? That means, what does that tell you about a in terms of slope? If you're thinking that a should be indeed m, because our two equations look very much similar, this m is in the same position as your a. The reason why this works is that you graph the x squared and you treated that as your x-axis instead of just your x. Notice how you dealt with it using the exponent. So taking your x values and taking it to the exponent that you see that's in the equation. When you're doing your experiment, you're not going to be given the equation. You need to graph your data, you need to look at which one of these graphs best fit your model in order to find the best way to linearize your graph. After doing this example, what I'd like us to do is we're going to try to find the slope of our graph and use that to find a, which is answering the question. I'm going to give us a second to do that. You may pause the video. Hopefully you had a chance to calculate the slope. And after me choosing 2 points, I chose 1 point being 30, 10, so 10 and 30. And this one over here being 30 and 90. Taking our slope, calculating for our slope, I get a total of 3 being equal to a. So that's the way how you can use the slope of your linear graph to help you derive the slope in your original equation represents your graph. This skill is important because knowing the slope, knowing what a is, allows you to figure out other things. For example, when you looked at the relationship between period and mass, there is an actual equation that governs that relationship. If you're curious, you can look this up, but period is equal to 2 pi times the square root of mass over k, something called the spring constant. So notice that if you plot m versus t, you get a slope, you get a slope that has to do with 2 pi as well as your spring constant. When you know the slope, that allows you to figure out What do these constants all mean? That's something we will take a look at later on. Before that, I'm going to give us a chance to do example number 2. Think about this. I'm giving you the equation. Take a look at the x. If x is under the square root, what do you think you should do with your x's before you graph them and linearize your graph? If you were thinking of taking the square root of your x values, then you are correct. So yet again, on this graph, for your first graph, you're going to plot your y versus your x. And the second graph, you're going to plot your y versus your square root of x. I want to try. And then at the end of that, figure out the slope of your second graph, and we'll come back together again. Okay, here below you see the finished work. After calculating the slope from your linear graph, you probably got something along the lines of 3.5, and if you were even more precise than I was, you may have gotten 3.46, etc., which is definitely more, I would be closer to the value of our slope. So indeed, in this case, our slope, our m, which is 3.5, is equal to, when we take a look at this equation over here, we can simplify that one to y is equal to a times square root of b times square root of x. Since we plotted the square root of x, our m would be the a plus the square root of b, which is a times square root of b. That is our slope. It's equal to a times square root of b. Many times you're not going to be getting the equation. I'm not going to tell you what the equation looks like. And in that case, what you have to do, you would have to plot your data, and from your data, figure out what is the best model for your graph. And that you can linearize your graph by manipulating your x-axis or sometimes even y-axis accordingly. Okay, so I'm going to give you a chance to graph this out. Same thing, graphing your y versus your x. You're going to try to see what kind of graph best fits your line. After that, you're going to take all your x values and convert them accordingly. When that is done, then you can plot your y versus your modified x value. So I'll give you a chance to do that and pause, so you can pause the video and we can come back together to wind things up. Graphing your data, your graph might look something like this. And looking back at your data set, or at the first page, the best model for your graph would be the y is equal to 1 over x, or x to the power negative 1. Which means, with your x values, you would want to take 1 over your x values so that you're able to plot on this side. You're able to plot that as y is equal to 1 over x. After you do that and find the slope of your graph, we can come back together and go over it again. So far, after we've graphed everything out, converted our values from x to 1 over x, we graph this out, we get a linear straight line. You may have noticed you were plotting it backwards compared to you were before. That's an interesting thing about these type of graphs. Looking at the slope, we find that the slope is equal to 2. Hopefully you have that. That means we can even write out the equation, the original equation of our graph. Because we know that the graph must be in the form of 1 over x, as this function over here. And since we have a slope of 2, that means if we have to write this guy as y is equal to a times 1 over x, that means the a must be the 2 as being the slope, which then gives us 2 over x. That is using linearization to even help you figure out the equation of your line. Hopefully you got something out of this video you can now use for your lab. Thank you for watching, and we'll tune in next time. Bye now.